Okay, so today we are going to discuss and proceed into a new chapter on additional analysis techniques. So far we have learned all the basic laws and principles in circuit analysis. We have learned about Ohm's law, we have learned about Tangerang's theorem, we have learned about passive sign convention. So if you forgot about this and the meaning of all of these basic principle, please review chapter 1. Then we have learned also one of the most important laws in circuit analysis, Kirchhoff law, yeah, which consists of two basic laws, Kirchhoff current law and Kirchhoff voltage law, KCL and KVL. Then afterwards, we have learned how to implement Kirchhoff current law in node analysis or nodal analysis, and with all variation of the circuit, yeah, with independent sources, dependent sources, then also with super mesh, etc., super node, etc. Then we have also learned about the implementation of Kirchhoff voltage law, KVL, in loop analysis and mesh analysis, including its implementation in circuit that contains only independent sources, then circuit that contain dependent sources, and circuits that needs to be analyzed using super loop analysis, yeah, as well as super loop, yeah, or loop analysis. So then today we are going to learn further on some additional analysis technique that might be beneficial to analyze uh, circuit, yeah, is more simply. So simplified analysis can be done if we implement these additional techniques. So for the sustainable energy environment and pharmaceutical chemical engineering students, you will be learning only until the end of this week, which is basically we will cover the topics on linearity and superposition, hopefully finished by tomorrow. Then for the biomedical engineering students, you will further proceed to learning about Thevenin's and Norton's theorem, and as well as maximum power transfer. So these four are what we are going to study in this chapter. So linearity is the property. We will learn how to implement linearity and then also superposition in linear circuit. Then using Thevenin and Norton's theorem. These are two very powerful analysis tools which allow us to focus on very specific part of the circuit. So we do not need to solve the whole circuit. We can replace the rest part of the circuit into an equivalent voltage source and resistor or current source and resistor. Then finally we will learn about maximum power transfer. Okay, so the methods of node and loop analysis provide powerful tools to determine the behavior of every component in a circuit. We have developed in previous chapter the combination, previous chapter, chapter 2, combination of series and parallel. We have learned about voltage divider, current divider, which are special techniques that are more efficient than general methods. However, they are limited applicability. So because voltage divider and current divider only apply, for example, for single loop or single branch, something like that. Single node or single branch. Therefore, they are limited. Then we learn about loop analysis and node analysis for more complex circuits with more nodes and with more branches. So in this section, we have developed additional techniques to simplify the analysis of some circuits. In fact, this technique expands on concepts that we have already introduced, which are linearity and circuit equivalence. So, for example, in the first slide, in the first picture here on the top, shows two resistors, which basically we can combine into a single series resistor. Yeah, this one, R1 and R2. And if they are in parallel, we can combine into R1, R2 divided by R1 plus R2, yeah, or 1 over Rp equals to 1 over R1 plus 1 over R2. So we have learned this in chapter 2. And actually, this is maybe something which we mentioned, yeah, in chapter 2, but maybe not. We want to emphasize again in this particular chapter. So when we have voltage like this, two voltage sources in series, so we can combine them basically into a single voltage source. Okay, so for example, if the overall terminal here is the upper part is positive, we consider it more positive than the lower part, then the combined voltage source becomes V1 negative V2 here. Here because V2 is drawn with the upper part more negative or less voltage, less potential compared to the bottom part. So that's why it is negative. So the resultant is V1 negative V2. Similarly, we can do the same addition of current source. The difference is that the current source, we can add them when they are in parallel. Yeah, remember, because from Kirchhoff current law, yeah, the current here, the total current here basically is the addition of these branches. Yeah, so I1 plus I2. However, since I2 here pointing downwards, so it means then the sign is negative. Yeah, which is shown here. So the two current sources become a single current source whose value of current is I1 minus I2. Then similarly, we can also change, for example, here, the bottom part, a voltage source in parallel with a resistor. Yeah, we can change it into a current source in series with a resistor. Okay, so something like this. So here, then, the V output at this pole compared to the negative part is basically V out equals to V source, yeah. Here, yes, V out equals to V source, and in this part, this is the current source is in series with a load or with a resistor, so the current output is equal to the current of the source. Okay, so then the models used are all linear. So mathematically, this implies that they satisfy the principle of superposition. So when maybe you will learn, I believe you will learn this, or you should have learned this in calculus, and later you will study the principle of linearity and superposition in more detail in engineering mathematics in semester 3. So the mathematical model, yeah, of a physical system Y equals to T U is linear if, yeah, when it is written with double F, it means that if and only if. Yeah. So if, remember, yeah, the logical, oh, sorry, the logical the logical lesson in high school. Yeah. So if it is like this, if it is just like this, for example, a condition like this is Y. If Y, then X. Okay, this is if. But if it is double direction, then it is if double F, yeah, which means actually if and only if. So it means this relationship is valid for two ways. So if Y, then X, as well as it can be also interpreted if X, then Y, something like that. Yeah. So that is the meaning of if with double F. Okay. So then, so a function or a model of a physical system Y equal to U is linear if and only if T times the alpha 1 U1 plus alpha 2 U2 equals to alpha 1 T U1 plus alpha 2 T U2. So for all possible input pairs U1 and U2, and all possible scalars alpha 1 and alpha 2. It means in different way, if we can express it, that the output of a linear system, which consists of a subsystem inside it, is equal to the addition of the output of the subsystems that makes or that forms that whole system. This is what, if we express in wording, in words, this mathematical expression. An alternative and equivalent definition of linearity splits the superposition principle into the model y equals to tu is linear if and only if t in parentheses u1 plus u2, so there are two input values, then this equals to tu1 plus tu2. So this is the principle of additivity for all possible input u1 and u2. And if we have t, the function of alpha u, a scalar multiplied to an input, this will be equal to the scalar alpha tu. This one, so it equals, the value will be equals to that scalar multiplied to the output of that function when the input is u. This is what we call as the homogeneity principle of linearity. Okay, for every this is read as every alpha and every u. Notice that technically linearity can never be verified empirically on a system, but it could be disproved by a single counterexample. It can be verified mathematically for the models used. So using node analysis for resistive circuits, one obtains model of the form. Remember the node analysis. We usually, after we derive the equation system, and we can put them into a matrix, right? In node analysis, what we are concerned of is to find the voltage or potential of each node, which is expressed as this column matrix V. Okay, while A is the matrix of the coefficient matrix from the equations, and F is usually the current, the current source or something like voltage source, something like that. So phi is a vector containing all the node voltages, and F is a vector depending only on the independent sources. In fact, the model can be made more detailed as follows. A multiplied by phi equals to B times S. A and B are matrices. S is a vector of all independent sources. For circuit analysis, we can use the linearity assumption to develop special analytic techniques. Now let's review the technique that is available currently. For example, here we have this circuit here with a single independent voltage source, R1, R2, R3, R4 with an output, the output. Okay, so we draw, in order that we can solve it better. So Vs, then this is connected with R4. The grounded node is this part, between the Vs and R4. This becomes the reference voltage. Then this is R3 connecting between this node, between R1 and Vs, and between R2 and R4. Then R1 and R2 are connected in series, and V output is the voltage across R2. Okay, this part. So from here we can solve using parallel resistor and series resistor, or otherwise we can use also loop analysis and node analysis. So after redrawing, we draw two meshes or two loops. So here from the first one, from starting from this node, Vs, this is Vs plus R3 times I1 minus I2. So this is supposed to be negative here. plus here R4 plus I1 equals to 0. Okay. Actually, this is supposed to be negative here because it is a voltage increase there to this node to here. There is a voltage increase, while we usually express in loop analysis voltage drop as positive. So on the second loop, R3 I times I2 negative I1 plus R1 plus I2 here, R1 plus R2, yeah, because they are in series equal to 0. And V output here, the values that we want to find is equals to R2 times I2. Okay. So from here, we obtain V1 equals to Vs, yeah, because here it is measured according to the grounded. So the voltage one here relative to the ground or references is Vs basically. Then from here V2 minus V1 divided by R1 plus V2. This is using node analysis. Yeah? This is using loop analysis, while this one is using node analysis. V1 equal Vs. So at this node, V2 at this node, V2 negative V1 plus divided by R1 equal to V2 negative 0 divided by R4 plus V2 negative V output here divided by R2 equal to 0. And then at this node, V output negative V2 divided by R2 equals to V output negative V1 divided by R1 equals to 0. Okay. From there, alternatively, we can solve using combination of series and parallel like this. So R equivalent here versus R1 plus R2 in parallel with this R3. So R3, R1 times R1 plus R2 divided by the sum of all the resistor, R1 plus R2 plus R3. This is the value. Then V equivalent here, V voltage at this part equals to this point towards the 0, R equivalent divided by R equivalent. Sorry, the voltage from across this point, this point to this point, R equivalent divided by I equivalent, R equivalent plus R4 times Vs. So this is a voltage divider formula. So from here, we obtain here, so V output is again another voltage divider formula, R2 divided by R2 plus R3. Actually, this is supposed to be R1, yeah? Yeah, sorry, another mistake. This is this resistor times V equivalent equals to 0. Okay. Using homogeneity principle, assume that the answer is known. Can we compute the input in a very easy way? Yeah, this is VE1 is the voltage across R3. If V output is given, yeah, then V1 can be computed using an inverse voltage divider. So V1 equals to R1 plus R2 divided by R2 times V output. Yeah, this is inverse voltage divider. And Vs using a second voltage divider, yeah, Vs equals to V1 divided by Req, yeah, times R4 plus Req, R equivalent of this resistor. Then from here, we substitute V1 with this value, R1 plus R2 divided by R2 times V out. So here, so from here, we can solve the variable V output based on variable Vs. Okay. So it can be made as algorithmic entirely. Give to V output any arbitrary value. V dash output, for example, equals to 1 volt. Then compute the result. So V out, we put 1 volt here. So from here, we obtain V dash S. Yeah. So there's solving the problem backward is easier. Using linearity, then from here we obtain Vs dash, which is equals to V output. From here, this is the linearity. From if we know the V output dash, then we can obtain K Vs dash. K here is constant. R4 plus R equivalent divided by R equivalent times R1 plus R2 divided by R2. Using the principle of homogeneity. So the given value of the source V underscore S is K, Vs divided by Vs dash. So then the desired output value will be V output equals to K V output dash, which is then we substitute the value of K here with Vs divided by Vs dash. So an example is like this, shown in this picture. Or maybe, since time is up, we will continue this discussion tomorrow. Okay, so let's stop the recording first.